All right. What we're going to try to do, get your clickers ready. We're going to jump right into clicking. Today we're going to talk about the quantum theory of the hydrogen atom. Now, I'm going to give you guys really, really basic stuff since the mathematics of quantum theory is way, way up there. And I don't care whoever is in this class, no matter how much calculus you've had, you're probably, you know, it's nice, but it's been nice knowing you. But if I took you through that calculus, it'd cause your brains to melt, possibly. But we're going to do some, so it's going to be show and tell level of quantum theory of the hydrogen atom, pretty much. But on Monday next week, I'm going to go over covalent bonding in terms of quantum theory. And for that, I'm going to go into some advanced stuff, but I'll tone it down so that you guys can hack it. Now, let's do a few multiple choice items. Turn on your clicker. Uh-oh, I forgot to turn on. Base is on. You should have Go Nitro. Okay, first question. Black body radiator. Look at that. Listen to that. The entire room goes quiet. It's exactly what I want. Think very carefully. Read carefully and think carefully. Can you guys make a count? Twenty seconds. 10, 9, 8, 7, 6, how much? 4, 3, 2, 1. Good. Okay. Yeah, we got a little bit of explaining to do here. The correct answer is C. And you know what, you guys, you know what they say on multiple choice questions? If there's a really long answer, there's a good chance that that's, you know. But what I did was option D. I put that in. I did catch a few of you on that. I tried to make that really, really long in option B, and I mixed in a bunch of gobbledygook. And then option A, I don't want to seem cruel, but you have to put in stuff to tempt you out of the, um, out of the correct answer. Option A, double slit diffractor. I put that because I have the question over it. But black body has nothing to do with diffraction. I mean, not directly. You could observe a black body with a diffraction grating, but not the double slit thing. So option C is the correct answer. And because it radiates perfectly, therefore you would also say that it reflects zip zap. It's a black body because it reflects no colors. That's the only way that you see a color. Okay. You know what? Nobody's in here wearing a color. This is Isabel. It's got to stand up, Isabel. Come on. All right. All right. Next question. Now this is about the diagram. This question is about that diagram and about what we talked about last time. "20 seconds. starting right now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys answered. This is another one we better do a little explaining here. We got a mixture of answers, and you know, the correct answer is A. And yeah, nothing special happens like doubling the wavelength and having to, you know, where that happens? That happens with electronics. I mean, you can, you know, you do splitting and stuff of your frequency, but you can't, you know, nature doesn't do that kind of thing, having the frequency and whatnot. So anything, whenever you see me saying double the frequency or double the wavelength or something, just think of that as trouble. And but plane waves, remember, we did this diagram here the other day. Um, remember this one? We talked about the plane waves coming in, and the relative size of the ball bearing was 8600 pixels, and you know, that's only 200 times bigger than the wavelength, and it should have been a lot bigger than that for the calculation that we worked out. So, so this is it's important for us to remember the relative size of things, wavelengths of light, and then the size of the object or the size of the gap that you're going through, if you're going through a diffraction grating or something. All right, next question. E equals HF. So this is two separate options separated by a colon or a semicolon, I should say. You know what that is? You know what this guy's wearing? That's a cravat. What he's wearing around his neck. That's a necktie. Those are the first neckties. The neckties that we have today are started their evolution from that state. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys answered here. Okay, good. The correct answer on this one is E. So if you, let me just check. Oops. Let me look at this. Yeah, a bunch of you chose A, and technically that is correct, but the best answer, of course, is this. And we'll be talking about that again today, because we're going to get into uh, the quantum theory of the hydrogen atom. Okay, Planck's constant. Twenty seconds. This should be really easy. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. All right. We got a real problem here. For those of you that voted for A, um, I don't know what you're doing. You're taking notes or sleeping on Friday, but yeah, this is the correct answer is D. This stuff up here, that's units of power, joules per second. That's a watt. Okay, and joules per meter, that's a newton. So that's a unit of force there. But that's not what Planck's constant is about. Joule, that's it, and nobody voted for that. Nobody voted for B or C. The only thing I caught you on was A. So you were thinking joule in second, but really, this is the one. Now go ahead and write down this vocabulary term, action. That's that is the physical quantity. Now we don't use it that much in elementary physics, in intro physics. But if you were a physics major, the next physics class you take, which would be Newtonian mechanics with calculus, yeah, you talk about action. And it has the same units as angular momentum. So, and I think a lot about that. Why is it that the Planck's constant, the one constant that rules the world, has units of angular momentum instead of energy? Why is that? And there seems to be a reason, and we're going to talk about it in a few minutes. Anyway, so that's how you can differentiate here. Now that unit 6.63 times 10 to the minus 34 joule seconds, because a joule can be converted into electron volts being an atomic size unit of energy, that's sometimes that will be a different value, but it'll be electron volt seconds. And so a lot of times people use that when they're doing atomic systems. But this is the metric system. And historically, the name of it is the quantum of action. Planck's constant, 6 point. And this is just 4 digits of precision. But if you look it up in the National Institute of Standards and Technology, NIST, you'll see, I don't know, another 3 or 4 digits that they know it to, or that they've measured it to. So Planck's constant, and you can convert it into electron volt seconds as well. Or, there's a zillion different foot pound, what would that be? Foot pound seconds or foot pound minutes, in the English system, but nobody would ever think about doing that unless they're, a maximum nerd for units. All right, now what we're going to, so that's just a little review from last time. What we're going to do now is also a blast from the past. We're going to redo the standing wave demonstration. I want you to take notes. Brad and Andrew, go ahead. The spring is up here. And we're going to do it a little more carefully. I want you to use the same positions, same area. And I want everybody to time it. If you have a cell phone, all right, get your cell phone out and use the timer device if you have one. Let's see, let me get my stopwatch. Okay. And give him a little bit more, Brad. Okay, good. Now, Brad and Andrew, Brad, I don't want you to move your hands from where you've got them clasped on the spring. All right, we're going to do a couple variations, and it's absolutely certain that you have to keep the same amount of tension. All right, so that means neither of you move your feet, and Brad, you don't move your hands. All right, so let's get the fundamental mode, and what we'll try to do is count 20 cycles. We'll try to time, so be ready to time 20 cycles with your stopwatch, and write it down in your notes. Okay, go ahead and get the fundamental mode. That's a little too fast. Hold up. Give him a little bit more. Okay, good. Go ahead. All right. Hold up. I want it a little bit slower than that. Give him a little bit more coil. All right. Let's try that. All right. Here we go. Now what I'm going to do is start it at the top. I'm going to go start. And you hit the start button on your watch. And I'll do the same thing. And then we'll count 20 cycles. And when it gets to the top, on the 20th time it gets to the top, then we'll yell stop. Okay, so here we go. Ready. Whoop. Let me get my phone here. Ready. It's still pretty fast. Okay, hold up. Andrew, step forward half a step. Okay, let's try the fundamental mode again. Okay, that's better. 1, 0, 0, 0, 0. Ready, and start. Oops, I forgot to do mine. Did anybody get one? Yeah. Ooh, okay, cancel. Can't reset. You guys keep oscillating. Brad, you just keep your hands where they are. Okay, ready. It's good. It's because it's fast. Ready. Let's see. Ready. No. Let's see. I got to go fast here. It's still too fast. Brad, give him a little more rope. Okay, good. All right. Get me that fundamental. This is slow enough for Dr. B. Okay. 1, 1. Ready and start. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Stop. Keep it going. All right, write it down. All right, and I'm going to do splits. Okay, let's do it again. Ready and start. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Stop. Okay, we should have Daniel. What do you got?
For the first one, I have 13 seconds.
Okay. Albana. Who's got one over at this table? CJ, you got it? Who? 12.98, so that's close to 13. Who's got one over here at the back table? 13.36. What do you guys got?
13.31.
You guys, Rachel Dupuy, did you time it?
13.42.
Okay, so we're getting about 13. So write down your numbers, okay, for your table. Whoever's got one, either use your number or, and let me write mine down. And I got 26.59 for 40 cycles. So
Oh, yeah.
that's what I did.
Yeah, I did 27.
All right. Oh. All right, so write yours down. Now we're going to do it again. And Andrew and Brad are up there. They're doing a good job. All right, now, can you time it? Okay. And because I'm fudging it, I'm messing it up here. Let me just write down my stuff. 26.59 seconds. Okay. So I'll count, and when I say start, start. Okay. So the official timer, Kendra, is up here, but I want you guys to do it as well. Okay. All right. Ready and start. 3. You know, cancel. All right, I gotta do a better job of counting. Okay, so what I'm gonna do, instead of saying the word start, I'm gonna say 0. And that'll give me time to then say 1 for the first cycle. Okay, so when I say 0, start. That's numeric for start. Okay. 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. Yeah. Did you stop at 20? All right, keep it going, boys. Let's do it again. So, if you stopped at 20, write down what you got. All right. Now, okay, so 0 means start, 20 means stop. Okay. 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. 12.97 up for Carly. Okay, write down what you got. All right. And now, divide your number by 20. No, divide each measurement. You've got several measurements of 20 cycles. All right. Divide each measurement by, and I've got one of 40. So use your calculator now. 26.56 divided by 40. Okay, you guys can relax. I think we got enough data. Okay. Who's got one at this table over here? Kendra, can you write down some of these numbers? You'll be the official recorder. And this is for the fundamental. Now you got Brad, don't move your hands. Okay. Every 20-second measurement that you took, who's got one from this table? Your measurement divided by 20. 0.6495. Okay. 0.6495. Okay, over here, Rachel, your table. Does anybody have 0.6315 seconds? And I think I probably shouldn't do this, but 4 significant figures is okay because we're using pretty good timepieces. Okay, Rachel Visa or Lindsay Visa, what have you got? Okay, 0.6535 seconds. Use guys in the back. 0.649. You getting all this, Kendra? Yeah. Seconds. Use guys. 0.637.
It's probably because I stopped there right as it hit the top.
No, it's all right. You're doing good. We're all in the same ballpark, if you notice. Okay, CJ, your table. Who's got it? Yeah. 0.635. Okay, great. Okay, Jordan, your table. Did you guys make measurements? What do you got? 0.6400. Okay. Up here at Brad's table, 0.645. Okay, you guys back here at Marlena's table. Who's got a number? Okay, 0.63. Hey, you guys, are you writing these down? Kendra's got the official tally. They're all in the right, they're all in the same ballpark, so we're doing good. What do you guys got?
0.6395.
Okay, 0.6395. And yo, all the way back in the back. Kara, you guys. Who's got one? Carly, what do you got? 0.643? All right. Can you calculate the standard deviation? Did you get that last one? 0.643? Can you calculate the standard deviation for that? All right, what we're going to do, Kendra's going to calculate the standard deviation, so that'll give us a plus or minus to use. All right, now let's do the first excited state. So this is n equals 2 of the hydrogen atom. Now this one's going to be tough, so we're going to do it. So reset your timers. And Kendra, let's do some timing. Oh my goodness. Okay, we're going to try to time 40 cycles. That'll give us a little bit slop. We'll cut the slop level down. If you ever hear engineers or physicists talking about calculations and the measurements are not that good, they'll use the highly scientific term slop. There's a lot of slop in that calculation, meaning there's a lot of plus or minus. Okay, I'm going to start with 0 again, and we're going to go up to 40. So when I say 40, I want you to hit your stop button. You ready? 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 20, 21, 2, 3, 4, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. What? All right, let's start with the guys in the back. Yeah. Carly, what do you got? 16.87? Kendra, what did you get? 16.87. Ooh. Genius. Star for the day. All right, so take your number, divide it by 40. All right. So 16.97. I'll do mine. What is it? 16.87. 16.87 divided by 40. Good. Now, Rachel, can you take the meter stick and measure the distance from the center of Brad's foot to the center of the meter sticks are over here. Yeah, just go ahead and grab her meter stick. All right, so let's get D. Okay. And it's going to be a 3 point something, but it's probably not going to be. It's going to be 2 point something. Wow, that's an interesting way to use it. 2 point what? .66? Okay, D equals 2.66 meters. All right, now we're going to do another one. We're going to do a variation. We're going to do the fundamental, but we're going to do a different D. All right, now Brad, do not move your hands. Andrew, I want you to take one big step backwards. All right, Rachel, remeasure. Let's get D first. Yeah, this is going to be over 3. It might even be 4 meters. Rachel, what's your call? 3.60? Okay, 3.60, so another meter. Okay, now what we're going to do is fundamental mode, and we're going to time out another 20 seconds. All right, so hit your clear button on your stopwatch. Let's do it one more time, and this will be the fundamental mode. Now, Brad, you haven't changed your hands, right? Okay, good. Now, what's going to be different about this spring now that Andrew has moved back a step? It'll be less what? Well, it might be a smaller amplitude. We'll just have to see. Of course, it can be, if Andrew does it right, he can make it pretty much any amplitude he wants. Well, not anything, but what else? What else is going to be true? Possibly smaller amplitude. Smaller amplitude might be handier to do. What else? Longer wave. Yeah, it's going to have. We're definitely going to have a longer wavelength because this is going to be lambda over 2. So our wavelength is going to be 7.20 for fundamental mode because the baseline distance is lambda over 2 for fundamental. What is true about the spring? It's longer. Therefore, what happens to springs when they get longer?
More tension.
Yeah, there's more tension. All right, so tension is going to be, so just make a note, more tension. Now we could measure it, if we had but we'll just write down the concept, tension is larger. Okay, give me a fundamental. And our code is 0 to start, look at that, and 20 to stop. You ready to go?
Yes.
You guys ready? All right, 0, 0, 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You got it? Caroline Lugo, what do you got? 1340. What do you guys got over here?
13.36.
Marlena's table, what do you guys got over here?
13.26.
All right, sounds about, so we're getting 13s, divide it by 20. And guess what? It's going to be similar. 13 divided by 20. Let's see if it'll be distinguishable from the previous 3.60. All right. So let's go around the table and we'll start over here at your guys' table. Who's got a period? What we're calculating is the period. You measure 20 cycles, the time, and then you divide it by 20, and that's the period for one oscillation. So the inverse of this will be the frequency. What do you guys got? I thought you had a distance, 13 point something, or a time. 20. You guys over here, what do you got? 0.6465 seconds. That's 20 cycles.
No, that was the cycle.
Well, yeah, that's from a set of 20 cycles. You guys got it yet? 0.663. Okay, Kara's and use guys. Carly? 0. Wow, this is. Okay, CJ's table. 0.670. Okay. You guys. I can't hear you. Okay, 0.6755. Brad's table. You guys let's give Brad and Andrew a hand. They've done a good job today. All right. All right. Use guys. What? And Christopher, what do you got? 0.665. Thomas, what do you guys got? Cassidy. 0. 0.665. I hope nobody gets 0.66. You did?
I did.
Oh, no. We better remeasure on that one. What do you guys got? 662? We're flirting with disaster here. Okay, Lindsay, what do you guys got? Okay, 0.667 Rachel Dupuy, etc. Et al. 0.663. And use guys, what do you got? 0.668. The first table was, you mean these guys over here? What do you guys got, Pete? Yeah, those guys were low, 6.465. Somebody jumped the gun on that. All right, but look, the numbers are the numbers, and we'll use them. Now, we've got a record up here. We're going to do some calculations with that. But because it's Thanksgiving weekend after hey, raise your hand if this is your last class of the day. All right, now, second. Grad students, it doesn't count. They never relax. Raise your hand if this is your last class of the week. Sweet. Sweet. So this is one of those weeks where Monday is Friday. We need more weeks like that. All right, so as I was saying, we'll try to get. I'll try to put the figures here in the YouTube that Kendra's going to calculate. Go ahead and calculate wavelengths and frequencies, and give me a plus or minus for the period calculation or standard deviation for period for each of those. And I'll take an order of fries with that too. Yeah. It just sounds like I'm just, well, give me this and I'll take 2 of those, and you still got the buy one, get one. And yeah, wavelength, frequency, and a plus or minus for the period calculation. That's our basic measurement. Okay, so now as I was saying, okay, you guys want homework or not? As I was saying, being this is the last day of the week for many of us, and especially since it's my last day of the week, we're not going to, and I'm sorry I said I would have weekend homework, and I wasn't, because the measurements, the YouTube measurements were, the video was nice, but the measurements were we didn't have enough precision to make a good homework assignment, but this will be good. So we'll make this into a homework assignment, but not over the current weekend coming up, starting today. So you won't have any homework this weekend except to read and stuff and think. Now, what you're going to be thinking about is the quantum theory of the hydrogen atom. And let's start talking about that. Now, if you know how to surf, you know that this guy in this picture is pretty brave, pretty highly skilled. But think of the photographer that got this. Now that is some skill, my friend. Clark Little, he gave me permission to use this. He's an awesome photographer. All right, so we're going to talk about the quantum theory of the hydrogen atom. That's a little bit of diffraction view. Remember waves. So this is what we think is, this is the Rutherford picture. Professor Rutherford from England figured out that matter, that atoms have a positive nucleus of some kind, various sizes, and a bunch of electrons that are orbiting it. Now, originally they thought that the electrons were like little planets, but when they and it's still a nice way to think about the atom because it reminds you of orbits and stuff. But the quantum theory doesn't permit us to think of electrons as little tiny planets orbiting a nucleus. Now, this is the simplest structure in the universe, the hydrogen atom. All right. You know, in terms of matter, this is neutral matter. It's just hydrogen. You know, 74% of the visible universe, something like that. Now, what we're going to try to understand here is this: that when they looked at the Balmer series, they thought, you know, they knew that if the electron drops down closer to the nucleus, it'll lose energy, and it'll be accelerating, and that'll radiate light. You know, accelerating charge is the source of the electromagnetic field. But it doesn't, the electron doesn't emit a full spectrum. It's not a continuous spectrum. It's only certain colors. So somebody said, look, let's think of it as being only able to drop a certain number of orbital levels. In other words, kind of like planes in a stacking pattern over a busy airport. They keep some planes at, you know, 15,000 feet and others at 13,000 feet and others at 11,000 feet, you know, so they keep them separated. So the electron only lives at certain specific altitudes and no others. And each altitude has a set level. I mean, it's a charged system, right? It's an electron and a proton. So if you know the distance, you can calculate the electrical potential energy, right? So if each of them has a certain altitude, you can figure out the electrical potential energy for that separation. You know, and we didn't really do a whole lot of that, but you know that you can do it. It's KQ over R, right? Or it's KQ1, Q2 over R. So it's KE squared over R for this simple model. All right. Now, what you do is you number the orbits. The lowest one is called the ground state, n equals 1. So you start counting with that one. Then the second orbit that's allowed is n equals 2. All right, and you know, a lot of times you would call that the first excited state. N equals 3. That's the next orbit. N equals 4. All right, and the quantum theory says quantum means a quantity, so it implies that something is countable, that it has integers underneath it. Now, the Balmer series is all about integers. They're all over the place. You know, it's 1 over 2 squared minus 1 over n squared, and you have to start with n equals 3. And guess what? That's explained by this picture. All right? So here's n equals 3 and n equals 2. When that n equals 3 electron dips down to n equals 2, it emits the red H alpha photon. E equals HF. So calculate its wavelength in the laboratory, and it's a photon. Therefore, calculate its frequency, F equals C over lambda. So the lab, you measure lambda. Good. Frequency, C over lambda. Good. Energy, H times frequency. Planck's constant times the frequency. So this we can measure. So the color of the light tells you the basically delta EPE between each of these levels. All right? You can figure out the energy of the electron from its color. All right? And then you put it all together and you figure out, okay, now we know the proton's got a certain, and you can, work out all the numbers and, and so here's your quantum leap. Yeah, that's what this is. This is a quantum leap. You've ever heard that term? It's like an old time TV series, I think. Is that right? Is that like back in the 80s? I don't watch too much TV, so I heard there was something called quantum leap. Anyways, this is a quantum leap that they're talking. This is a quantum leap. This is not a TV show. This is happening all the time. And when we were looking at the spectrum of hydrogen the first day of class, that was the brightest line that we saw. N equals 3 down, N equals 2. And bam, here goes the red photon outgoing. So you number the orbits, and as an electron drops to the lower EPE orbit, it loses some energy. So we don't think of it as going into kinetic energy, and you'll see why that's the case as soon as we introduce waves. But it does, the photon carries off the missing energy. So you're losing potential energy as you go closer, all right? And that goes into the energy of the photon, all right? So that's the rudimentary quantum theory of the hydrogen atom. Now, there's problems with this. There's unanswered questions with this. But it does jive with, Balmer's series, and it does jive with all those wavelengths that were measured, at the wazoo. They add them, the wavelengths, to a trace. Yeah.
You were saying the photon when it's released doesn't have kinetic energy, or it's not.
Well, the photon has energy, HF.
Okay.
It's the electron. We think of the missing electrical potential energy as going into the photon instead of the kinetic. So when a basketball drops down, it doesn't radiate any energy, nothing that we can see. Okay. So all of its energy goes into kinetic energy. So it drops a little potential, gains a little kinetic. All right. But in this system, we think of all the missing energy as going into the photon, HF. Okay, so we measure the color, we measure the wavelength, get the frequency, get the energy. So we get those energy gaps, and basically that's what you got. You got a bunch of energy gaps if you can measure all these levels, and which we did. So here are the guys that, as I mentioned last time, that figured out almost all of it. Niels Bohr and Albert Einstein and their buddies, their friends, and I'm sure they talked with a lot of other people. But this is actually a wave equation, equals HF. So they're thinking about Planck's constant maybe, or maybe they're thinking about, maybe Bohr is thinking about, well, should I grow a mustache or not? Whatever they were thinking about, they knocked this into shape. They got it. Pretty good. Niels Bohr is the one that figured out most of it. And Einstein figured out the photon angle. And so this is called the Bohr, what we just looked at is called the Bohr model, B-O-H-R. Now, it's not fully quantized yet, because one of the things about this is how do you select the orbits? All right, we've got different colors. We know there are certain orbits, but how does nature decide that? It's not random. There's certain energy levels, but how does nature decide how far out to park the N equals 2 orbit? What's up with that? That's what we got to try to figure out. Why is there this granularity in the atomic states? And Einstein and Bohr and all those guys, Planck, they were all thinking, what is going on with this? What's up with this? We got all these numbers. They do seem to work. These are orbits. It's lovely. It's nice. But how does a planet, they were all thinking about, you know, little planets orbiting a nucleus. And because, for us, we can have a satellite at any orbit that, until it gets too close to the Earth and it'll break apart. But, the moon could be twice as far out and be perfectly happy as a clam out there. So in a classical system of Newtonian physics, there's no problem with different orbits. But in the quantum system, for some reason, only certain orbits, and we didn't, nobody knew why that was until Louis de Broglie in after World War II. He was a French guy, and he spent his war probably decrypting German messages at the radio station underneath the. He was stationed at the Eiffel Tower. They had a big radio receiver there, I guess, listening to the German frequencies. Probably they say that he worked in radio, but so what that means is probably he was decoding and deciphering as much as he could. But he said, "Look at this. The photon. We think of that as a wave. Everybody knew that light. You had to treat it as a wave as well as a particle. Okay, so light is this thing that exists in the world, and it doesn't think of itself as a particle sometimes and as a wave. The photon thinks of itself always as a wave that's also a particle simultaneously. Now we can't see it as a wave if we see it as a particle. If we measure a particle property of the photon, we won't see its wave properties. If we measure the wave properties, we won't be able to see the particle properties. So the particle properties are like, for instance, a well-determined position or a well-determined momentum. That's nice. You can do that with photons. E equals hf, no problema. But how do you get, if it's a wave, you can't, once you do that, you can't see diffraction effects and vice versa. So it doesn't work. So you can't see wave and particle things at the same time. So to us, it's like the argument between Newton and Young, Newton and Fresnel. Is it a particle theory or is it a wave theory? And the photon, a photon would come by like that cat and say, both, and it's at the same time, both simultaneously. So what de Broglie said, well, why don't we treat the electron the same way? We know that it's a particle. We've studied that thoroughly. How about if we treat it as a wave? So what de Broglie decided, and Andrew and Brad here were not around back 100, this was 90 something years ago. So he had to use his coconut to figure this out. I mean, he didn't have any lab assistants like that. But he said, look, think of the electron as a wave that curves around its orbit so that it always constructively interferes. Now think about that. It's just like what we had, except those guys were in a linear arrangement, point A to point B and back. But Andrew was generating waves that interfered with themselves. And that's how you form a standing wave. So de Broglie said, let's think of it as a standing wave with constructive interference. And that, my friend, will only happen at certain radii, and therefore only certain orbits. And just like Andrew, if he didn't have the right frequency, he wasn't going to get the right wavelength to form a standing wave. I mean, he could send waves across, but it looked all chaotic. It was all scrambled up. All right. But when he hit the right frequency, that meant he had the right wavelength, and bam, he had those nice standing waves. It's kind of tricky, isn't it? Getting it. All right. So this is what de Broglie said. Look, let's use the Brad and Andrew theory. Think of those electrons like standing waves. So you can see n equals 1, that little teeny one down there, a bump and a dip, alternating with a dip and a bump. All right, that's 1 full lambda. The next one, n equals 2, that's 2 bumps and 2 dips, alternating with 2 dips and 2 bumps. And the next one out, it's 3 of each. All right. Now, the thing is, this is not new. Thinking of a standing wave in this way, it is not new. And if you think about a guitar, you raise your hand. I know there's people here that play guitar. Raise your hand again if you play guitar. Okay, a bunch of you. All right. So if you're playing a guitar, you have a certain distance from the bridge down to where either where you put your fingers or the what do you call that thing at the very end?
That's the bridge, the neck is the top. Bridge.
Yeah, bridge to neck, or from bridge to wherever you put your fingertips. Okay, you form your own wavelengths. Okay, but only certain frequencies are generated. As soon as you put your finger down, you get a certain note, right? Certain pitch, right? So there's no problem with this. And so thinking of an atom like a quantum guitar that's not strung out linearly like this, but circling around, that's it. That's the wave theory. And it works great. Now, de Broglie said, this is the wavelength formula that will work. This is his relation. Lambda equals h over momentum mv. All right? He said, let us think of the electron as a wave, and let's think of its wavelength as related to its momentum, h over mv. And using that formula, h over mv. So Planck's radiation, Planck wasn't thinking about waves. He was thinking about black body radiation, and he did it. He nailed it. But it just so happens that this also controls the wave theory of hydrogen and every other atom. Now, this is the easiest atom to tackle. If you go up to helium, it's very tough. We're still working on helium, trying to figure out helium. A lot of properties for helium. So here's how it goes. The momentum state controls the size of the wavelength. Okay, and this is what we know about energy and orbital size. If you tell me the orbital size and you know the charges, ding, you got the energy and therefore the momentum, right? So automatically, so knowing lambda and knowing momentum, ding, you got it. And all that. Now, the things that controlled frequency and wavelength for Andrew and Brad were the tension in this coil and the mass of the coil. Okay, if we used a different kind of a coil, we would have had different wave. They would have had to oscillate faster or slower to get the fundamental state. Faster or slower to get the first excited state stuff. But for that spring at that time, that's why I told Brad, do not change your hands. So I wanted that same they're not going to change their feet. And I didn't want them to loosen up we saw them loosen it up a couple times. Okay, but once we got it set, I didn't want him to loosen it up any further than that. And he did. All right. Now, all right. So de Broglie came up with this theory. And you know what? He was a grad student. He was writing his PhD thesis. And his thesis advisor said, man, this is wild. I'm going to send this to Einstein. And he'll tear it apart. Except Einstein loved it. He said, this is fantastic. And so de Broglie, right out of grad school, he gets the Nobel Prize. Pretty nice, Andrew, huh? Yeah, it's like 2 years later. But it's better than President Obama. All right, he had to be in office for a few weeks before he got his. Anyways, so here's the next question. All right, Professor de Broglie, Mr. Big Stuff. Electron is a particle. It's a wave. But will it diffract? You know, particles can't diffract, but waves can. So if this electron is really a wave, if it really has wave properties, have you ever seen it diffract? So this is like the opposite of Poisson. Poisson was saying, yeah, okay, it's going to diffract, so what are you going to do about this? So these guys were saying, all right, de Broglie, go find me that dot. But he didn't have to, you know, because the guys, um, so the guys that figured it out were a couple Americans, Davison and Germer in 1927. They saw it. They weren't even looking for it. They were just ramming electrons through a crystal of nickel, crystals of nickel, you know, kind of ground up nickel. And this is the diffraction pattern they found. That's a diffraction pattern. And actually, this is a modern photo, black and white photo. But this is aluminum crystals, and that's what you get. They saw that in 1927, and they were talking it over at one of their science meetings, and they were saying, we got this weird distribution of energy. We got electrons going here, we got electrons going there. It looks like they're spreading out. And so somebody said, you know what that is? That's diffraction. Because Professor de Broglie over in Paris, France, said it's a wave. You've got waves activity there, my friend. So these guys got the Nobel Prize as well. Davison and Germer. Here's their original article. And that's December 1927. All right, that's their original. See, look at that. The intensity of scattering of a homogeneous beam of electrons of adjustable speed. Look at that. Adjustable. Look at the article. Look at the article. Come on, not on your phone. Look at the article. Look at the wording. Adjustable speed incident upon a single crystal of nickel. Adjustable speed means adjustable momentum, right? But look at that word they use, intensity of scattering. See, they were thinking of it as a ricochet. They were thinking of a particle going in and getting deflected by, something. But it wasn't. It was diffraction, all right? And you can read about it. You can actually look this up. Here's a pull quote. Equivalent wavelengths. Let me magnify this from there. Equivalent wavelengths of the electron. See, now they're thinking electron wavelengths. May be calculated from the diffraction data in the usual way. These turn out to, see, in the usual way. D and L and theta and trig. Yeah, they got a wavelength. These turn out to be in acceptable agreements with de Broglie's relation, H over mv, of undulatory mechanics. Undulatory, that means, that's an old-fashioned word for waves. All right, so here's some diffraction patterns. This is electron diffraction. You send it into a crystal, depending on the orientation of the crystal. See, this one's 3 different orientations. Same crystal, 3 different orientations, you get 3 different patterns. So if you get a bunch of patterns like that, you can analyze them and figure out the structure. Now, here's the most famous analysis of diffraction. Of course, this is X-ray diffraction. That's image 51, photo 51 from Rosalind. What's her last name? Rosalind Franklin. Yeah, Rosalind Franklin. She's the one that nailed the DNA structure. Now, there's somebody that got ripped off. She's the one that nailed it, but because she died of cancer very, very early in her life. So by the time they gave out the Nobel Prize for this photo, it went to a bunch of other guys, not her. Yeah, Crick Watson and one other joker.
I think they revoked it at least one point.
No.
Wasn't it like a race?
It was a race. Crick and Watson basically stole this image and used it. They didn't have permission to use it. But she was dead. Her lab assistant gave it to Crick and Watson behind her back. She would have given it to him, but probably. I mean, because you share scientific data. It's not like your propriety. Well, this is the only picture that there is, and I control it. No, she would have shared it, but He basically kiped it. Anyways, so she got ripped off, but that's why I usually never mention those two guys that you mentioned, Thomas. Yeah, the one that was C, his name begins with CR, and the other guy WA, and they're the ones that they got all they became rich and all that stuff. Bunch of thieves, in my opinion. Anyway, so here's the one thing that we got to remember. You know, this Planck's constant, the one constant to rule them all. I mean, it's everywhere. It's just like Fokker. Fokker, I'm everywhere. Planck's constant, it's everywhere. You know, he was thinking about thermodynamics. You know, and Planck was thinking about, and de Broglie was thinking about hydrogen atoms. It's everywhere. So here we go. Here's a synopsis. Spectrum of hydrogen, the simplest of all the atoms. Okay, H and delta EPE select the orbital size. Orbital size controls photon wavelength, frequency, and E equals HF. All those things that we can measure in the lab. Now, we're going to do some calculations. Have your clicker out. We got another few minutes to work. I want you to jot down this set of ellipses, concentric ellipses. And I've shaded them in so that you can distinguish between different areas. Now that's called a phase diagram. On the horizontal axis is position of an oscillating system, and on the vertical axis is P, the momentum of the oscillating system. That's a phase diagram. And what we're going to do is use a phase. Now that's for a simple oscillator, you know, like a spring mass system. All right. But it turns out that diagrams of this kind are also an excellent way to explain, in a fairly simple way, the phenomenon of quantization. All right. But before we get into phase diagrams, we'll probably tackle that on Monday next week. Let's calculate the Broglie wavelength first. All right. So let's do a couple lambda equals h over mv calculations. All right. So get your calculator out. And so here's some physical constants. I mean, you can look them up. This is from 2013, I guess. Speed of light in a vacuum, Planck's constant. And then Planck's constant reduced, h over 2 pi. Use that one a lot. Electron charge magnitude. There's a couple. Electron mass, proton mass. And look at all the digits for the electron mass. You know, all those things. And of course, the speed of light is exact, considered exact now. But look at Planck's constant. They've got 4, 7, 9 significant figures on that. So that's pretty nice. And then h bar, that's h divided by 2 pi. We're not going to be using that, but. All right, so let's work on a moving proton. All right. So here's the mass of a moving proton. Okay, 1.673, you know, from that previous page, times 10 to the minus 27 kilograms. All right, now let's move it at 5% of the speed of light. All right, and we can do that. It's easy to do. We can get protons moving. Because a proton, if you can get an isolated proton or a stream of protons, and you have an electric field or a magnetic field set up just right, like in one of these big accelerators, big atom smashers, yeah, getting up to 99.99% of the speed of light is no problema. So 5% is a walk in the park, 5% of the speed of light. All right, so there's our MV. So what we're going to do is calculate the proton momentum. So make sure you have those down. And let's see. Now I want you to put down, I want you to hit the refresh key because we're going to go to alphanumeric answers. All right. All right. And here's the same data. All right, so here's your data. So go ahead and type in, calculate, and then type in the momentum of the proton. And then when we get this, we're going to calculate lambda from, you know, h over mv. We're going to go h over this result. So get this result down. calculation. And hey, you guys, we're not going to be able to dodge scientific notation. I mean, now we're down in the nitty gritty. So you got to know how to use scientific calculation on or scientific notation on your calculator. Boy, am I ever great? Am I ever? Hey, they erased it, Andrew. Those, Nika, go to that blackboard. Here, come up here and take a marker and write TJIF on that blackboard, on that marker board back there. In big letters, TGIF. This is an outrage. We had TGIF on the marker board back there. Somebody erased it.
Because I mean, the wavelength would be the distance from their feet, right?
Yeah, for fundamental, it's twice the distance, and for the first excited state, it's exactly the distance.
And what we talk the time over those cycles is the period.
Right. So 1 over that is your frequency.
Yeah,
so
so
frequency times d or 2d is your speed.
Okay.
So your speed of propagation should be consistent. Thank you.
But that should still line up. Or that's light. That's the speed of light. So no, it shouldn't.
Yeah. No, you don't want speed of light.
I know.
Because
I mean, I work only with light, so that was my brain. I was like,
what? This isn't
C
working?
over F. I was like,
No.
what do you mean 202 million years?
Good one, Kendra.
That's not right at all.
Good one. All right. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, get your answer. Let me see what you guys got here. Oh my goodness. Everybody voted for C. Unbelievable. But also, so all I have to say is psych. All right. So, anyways, so when you're talking about a proton, 10 to the minus 20 kilogram meters per second is, a righteous neighborhood. All right. And that's a small fraction of an everyday, a baseball. That's a small fraction of what a baseball would have. But for a proton, yeah, that's not too bad. All right, here we go. Let's calculate a de Broglie wavelength. All right, now here's what we're going to do. All right, I'm just going to trot you through this. We'll do a calculation of this in a second. Okay, so we're going to go H over MV, H over our previous result. And so there's option C, which everybody wrote. So there's Planck's constant on top, 6.62607 times 10 to the minus 34. Now notice that on top there, I have joule second expressed as kilogram meter squared per second. That's the same. That's the unit of action or angular momentum. All right, or joule second. Now the reason that I do that is because we're going to do a little bit of cancelization. All right, so let me move this to the next page. Just going to move it up a little bit. All right. So there's and now let's do start canceling. All right. Kilograms, bing. Per second, bing. 1 unit of meters in the bottom. one on top. And so we're left with 1 unit of meters on the top, and that's good because we're trying to figure out a wavelength. Good. All right. So we want lambda to come out to some number of meters. Now we just got to calculate this baby. All right. So it's going to be 2 point something times 10 to the minus 14 meters. All right. And go ahead and calculate that. This is the easy part, you know. So we're not going to be doing, on the final, you may find something like this. I'm not saying what's going to be on the final, but you may find something that reminds you of this in a multiple choice question. All right. So anybody come up with this? 2.64. All right. Now here's what I want to mention to you. That 10 to the minus 14 meters is way smaller than an X-ray wavelength. All right. And because X-rays are a few nanometers, maybe a few hundredths of a nanometer. Now those are good for big things like molecules, DNA molecules and stuff, and other molecules. But for a proton itself, you need a lot smaller probe. So protons, we think they have a structure. We're pretty sure they have a structure called quarks, but it's very hard to get pictures of that. Now let's try a couple wavelength calculations. And this next one, hit refresh, please, because this one's going to be numeric. Okay. And this is an electron.
Okay. So I calculated for all three. The very first one, the 20 cycles with the 2.66 across, since that was the one cycle, I multiplied by 2. And then I did the 40 cycles, and that's just lambda because that one. And then I did the new meters with the 20 cycles.
What's the plus or minus on the period measurement?
What does that mean? Plus or minus on the period measurement?
Standard deviation.
The standard deviation of the first one was
Yeah.
0.006.
Good. Good. So that's 3 figures out. Yeah, do that one, and we'll publish that.
Do you want me to write it next?
Yeah, it's all on one page, right?
Yeah.
Okay, good. I'll take a photo of that and we'll put it on Instagram.
Okay. It's not very pretty, but
Doesn't have to be. The numbers do the talking. Yeah, be careful with. So this one I'm giving you the momentum, so it's kind of cinchy. Oh my goodness. Who said that? I just want to sleep.
me too.
That's like everybody in here, I think. I had a very hard time knowing that this was Friday, a Monday and a Friday. I had a very hard time to getting out of bed today.
I'm seriously excited very hard time.
Yeah, you better get healed up before finals week, my friend.
Trying. Like, it sucked because I was out. Like, I didn't go to school. I didn't do homework. Like, I was out of
Boy,
commission for like
bad
a whole
strategic
weekend.
time.
Like
Yeah.
4 days. That's way too much for me.
Yeah, you're gonna have to hustle and bustle to get caught up.
I know it's awesome.
You're gonna have to be very careful. Well, after next week, you won't have to worry about this class anymore because you're not gonna help with the final.
Well, the thing is,
This is the main
Don't worry about the final.
eyebrow, really.
I mean, I did all my professors moved my finals up. So I have final next Monday, Tuesday, and Wednesday. Before
Use
finals
the
begin.
time. Yeah, use the time. Oh, what?
Yeah. So like you're gonna have class on Monday?
You want me to go have a little chat with those?
My mom said the same thing.
Me and Andrew will go over there. Andrew will hit him high. I'll hit him low, just like this,
He was like,
right in the bread basket.
it was gonna be because he needed to go out of town. It was because he needed the extra week for that week
What a.
Like, I don't have time to do that.
Who
I
was
know,
that?
it's stupid.
What teacher was
I'm
that?
not.
Oh, I should track him down like Chinatown. You shouldn't do that. It's not right. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, brother. Okay, well, it looks like almost everybody got it right. 0.025 is your wavelength. Um, and it's also a small fraction of a nanometer. So just keep that in mind when you're doing these. Now here's the calculation for let's just go over this real carefully. H over P, standard, standard, standard. And then I converted that 10 to the minus 23 in the denominator into 10 to the regular 23 in the numerator. And so this is what you do if you're doing it on pencil and paper, you forgot your calculator. You just write it out and handle your scientific notation. And so 10 to the minus 34, or 10 to the 23, that's 10 to the minus 11. And then you got 6.63, you got some cancellations to do. And there's your calculation, 6.63, 2.65 in the denominator, 10 to the minus 11, and then meters. And then that works out to. And note that this is on the order of the size of a smallish atom. So for electrons, constructive interference and diffraction in terms of an atom is going to be an observable thing. All right. Now let's try one more object, and this is what we call in physics a paperclip. Okay. And the reason that all physicists know about paperclips is that theoretically, an object with a mass of 1 gram, a typical object, is a paperclip. So they always say, all right, 1 gram is about the mass of a paperclip. All right, let's do it. All right. So a paperclip has, all right, now this is a little bit bigger. A mass of a momentum of 2.65 to the 10 to the minus 3 kilograms meters per second. All right, now let's do this numeric as well. All right. Now this was going to come up with a way different number. Calculate its wavelength using the de Broglie relation. All right, so let me just make sure that you pay attention to that example very carefully. All right, so take a minute to calculate that.
Yeah, I got in trouble with last week because we had this thing for the physics LA class that we have to take.
Yeah, yeah.
Where we have to do an outreach project. I had mine planned for Thursday.
And you were sick as a dog. Nice going.
I know.
And it always happens this time of the semester. That means that last 3 or 4 weeks you haven't been eating good and sleeping good.
Well, I've been trying.
No, no. Well, you're a good student, so you're trying to work hard. That's what happens when you don't balance it. It's happened to me too. I mean, I've gotten hit by stuff.
The thing
But
is, this semester is the one that I've like worked the least, not like the least hard, but I've balanced everything to where I have relaxing time. Like I've been able to like have a day on the weekend where I don't do any schoolwork most of the time.
nice.
I know. So like the
That's
fact that I'm
really
like
good.
sick and everyone's like, Kendra, you're burnt out, and I'm like, no, because I'm making sure I have a day. You know?
That's a wise, boy. That's a luxury.
Yeah,
If you can do that, get everything done and still have that.
I mean,
That's a big luxury.
I'm at school for over 12 hours during the week, so like, I just want to work it off.
Yeah. Well, just for the sake of your mental sanity and stuff. Yeah, that's good. I'm glad you were at least able to do that. 1 minute.
Although this weekend I had 4 or 5
Well, we got Thanksgiving Day. We got this weekend. You know, a lot of people in here have the rest of the week off. I can't believe they gave us Wednesday off.
I'm so happy about that. 'Cause normally, I mean, normally I take it off anyway, but I have to email all my friends.
Yeah,
So I just emailed you a pretty good picture of the
you did?
on web places. Yeah.
Okay, good.
I don't get it. I mean, I have a pretty good camera. So like,
That's lovely. Very nice. This has good light.
yeah. I also cut myself with a kitchen knife. That was fun.
What were you making? Lemons or something?
Yeah, I was washing dishes and I looked away and I sliced my hand.
That's no good.
Making like I think it was for onions.
Lemon slices. Oh, onions are really good for you. And garlic, prebiotic. That's why I eat them. I try to eat them every day. Yeah. I know. Make chicken soup. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you. Oh my goodness. I just can't stop you guys. 2.5 times 10 to the minus 31. So look, so this, now a paper clip is 1 gram, right? So this is basically a paper clip going a few miles per hour. Its wavelength is 10 to the minus 31, all right? So a wavelength of 10 to the minus 31 meters for this macroscopic object of mass 1 gram is extremely small. 10 to the minus 31 meters is way, think of how big your pocket would look. You know, you put a paper clip in your pocket, or you put a paper clip in your pencil case. All right, that's like, you know, 7 or 8 centimeters. Now think of how many times this lambda is smaller than a pencil case, or your pocket, or your left earlobe. It's way more. You know, think about the plane waves and stuff, and the ball bearing, and that was, I couldn't even get 200 times bigger than the wavelength. This is 10 to the 30 something times bigger. Your pocket or your pencil case or your earlobe is 10 to the 30 something times bigger than the wavelength of the quantum wavelength of the paperclip. So that's why diffraction effects will not be observable for macroscopic objects like a paper clip or like you. Now, if you were an electron and that door was a nanometer or something, then you'd diffract. You know, electrons would diffract through a door, a gap of a nanometer or so. Your wavelength is even smaller than this because we weigh a lot more. Each of us, we weigh a lot more than a paper clip. So our wavelength going through that door, that door is about a meter wide, right? A little bit less maybe. So we'll just round it off to a meter. And you're talking 10 to the minus 30 something meters for your wavelength? Forget it. You're going to be little teeny plane waves marching through a gap. You ain't going to get jack for diffraction. Sorry. And think of the flash. Is he in the Marvel Cinematic Universe? He's DC. He's DC. Okay. Think of the Flash. I mean, I see my son watching the Flash on TV, and I think this is such garbage. But I've it's like a soap opera with science fiction fantasy like, oh, well, and everything's like drama. Anyway, but I get this idea that Flash is able to go really fast, right? Something like that. So Flash is going to go zapping through that doorway, and he's going to get even less. Yeah, he goes like this, and he's going to get even less diffraction. So now let's do the dot cam. Let's do some phase space activity, and we'll just do some sketching here. Oh, can you give me my pencil? Give me that. Oh, that pen there is yours. I stole it from you about a month ago. Yeah, I temporarily borrowed it. What? What did you say? You kiss your mother with that mouth? What a. I just don't know about you guys sometimes. All right. Shh, 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 shh. All right. Now what we're going to do here is we're going to make a sketch of phase space. Now, as I mentioned, I'll go ahead and draw some horizontal and vertical axes. And the position X and the momentum related to that, so the X component of the momentum is the vertical component, or is the vertical axis. All right? Now, I want you to go side to side and mark out equal. I'm going to make this a little bit further out. Okay? So this is X max. So so this is like an oscillator system. And we know that an oscillator will go out a certain distance on the x-axis, and then it has to come back. And then it scoots past equilibrium. Here's equilibrium right here. Okay, the origin of the phase space system. Okay, now here's minus x max out here. All right. Now, where is the spring mass system going the fastest? At equilibrium, as it goes through x equals 0. So you have up here and down here P max and minus P max down here. Now these should be equal in size. For a regular oscillator, they will be. Now what I want you to do is trace in an ellipse. Now an ellipse is going to be vertical, it's going to be tangent to these verticals, tangent to these horizontals, so you can kind of trace in. And actually, I'll just trace in a whole box here, a rectangle. Okay, the ellipse is going to go inside this. All right, so it's supposed to go here. Then it curves around, just flat here. It's flat up there, but just for a second, because then it starts dipping down over here. And by the time it gets to here, it's vertical. Okay, and so this is what. Now the direction of time is encoded in a phase space. So let's just think about this for a minute. Let's say that this is x at times t equals 0. So x of 0 is here. And you let it go. Now it's going to travel to the left. It's going to head out for minus x max. That's going to be half a cycle later. All right. And so it's going to have negative momentum. It's going to have negative velocity and negative momentum. So it's going to go to this point first. This is maximum leftward momentum down here, minus P max. Let me get that minus sign a little bit more. All right, so here's the arrow of time. In this case, it's clockwise. All right. So then it goes to maximum compression here. So this is max compression. Here. And then it starts getting positive momentum. So this is max compression. And so maximum force here, acceleration is greatest. And so you get started getting rightward. So this is max rightward momentum up here. And it goes rightward until it gets to maximum rightward position. Okay, so this is max extension. So this is thinking about it in terms of an oscillator. Now, if you have go ahead and draw in another ellipse and make it kind of the same proportions. All right. And I'll do, I can't find my red. Oh, here it is. Okay. So I'll try to do this in red. And you can, all right, so here's that's a little bit sharp there. Try to straighten this out. That's better. Okay. So here, this one has energy E2. So, you know, in an oscillator, the total energy of the system is equal to 1/2 K times X maximum quantity squared. That's the total energy of an oscillator system. It's also equal to 1/2 times 1 over M times P max quantity squared. So these two numbers are the same for a standard mass. Now, we don't usually work with momentum like this, but we certainly could. Now, let me add, so there's two different max momenta, and you can describe each one as having an energy. All right, each one has a maximum momentum, each one has a maximum extension. Now, this is for the same value of K. All right, so let me ask you a question here. Which of these ellipses, the inner or the outer, has a larger total energy? Which one has a larger total energy? The outer or the inner? Outer, you think? Why, Krishna, why outer? I saw you nod your head. It's got a larger momentum. This is a larger momentum up here. It gets a bigger P max. So go ahead and write this down. E1 is greater than E2. And guess what, my students? the area of any of these ellipses, it's equal to uh, pi times semi-major axis times semi-minor axis. So that's x max times p max. All right, so that's the area. And guess what the units are? What's a momentum times a distance? What's that the units of? Momentum times a distance. Kilogram meter per second times a meter. It's units of action. And guess what also has units of action? Planck's constant. And on Monday, I will show you how Planck's constant and these areas are related. You're dismissed. I'll see you on next week, next Monday. And we'll close up the semester. Now, let me see if I can get a... You know what? Is it true that Instagram turns everything into a square picture?
Yes.
They suck. I've been putting everything up there without making it square. So I'll just take a square picture of this. You know, Kendra.
Yep. You want me to take a picture?
No, I want to do it, but this one. They come out with shadows. Let's see if I can do this. Right. Yeah, see you later, bro. All right, so this one, and I'm gonna. Okay, so this is blank. Can you put this back over? And then these are my notes. Okay, let's get this stuff put away. Let's terminate the YouTube.